going to examine what transmission line voltages look like in sinusoidal steady state. This is important because we know by Fourier that we can represent any wave as a sum of sinusoids, which means that a good understanding of sinusoidal steady state will let you understand every wave you run into. I've drawn a circuit that could result in sinusoidal steady state voltages on a transmission line at the top of this page. You can see V in of t is a cosine wave here, and we'll make a mathematical formulation of it on the next page. The wave has a period of 4 nanoseconds, which is the same thing as saying it picks up 2 pi of phase in 4 nanoseconds. And that's how we calculate the angular frequency. We're also saying that V in of t has a 0 to peak voltage amplitude of VZP. I've drawn V of xt for a few different values of t to show how this V in of t propagates down the transmission line. We can see at time 0 that the V in of t sinusoid has propagated everywhere on this infinite transmission line. The fact that the sinusoid has already propagated an infinite distance at time 0 might trouble you, but this is just a standard consequence of sinusoidal steady state analysis. We assume the sinusoidal drive has been going on forever when we do this kind of math. The x dimension of the sine wave has been stretched by the velocity of the transmission line as usual. You can see that stretching by looking at the first peak of the 0 nanosecond curve, so right here. It's at 40 centimeters, which is 10 centimeters per nanosecond times the 4 nanosecond period. The amplitude of the wave is VZP everywhere, the same as V in of t. That's because we have a source impedance of 0 in this example, so the divider between the source impedance and the driving point impedance has a magnitude of 1. That's because Z0 over Zs plus Z0 is 1 if Zs is equal to 0. In a general case, the 0 to peak voltage on the line will be set by the source divider. There are a few different ways to look at the time evolution of these voltage distributions. If you look at the peaks of the distribution, you can see the waves are propagating to the right at 1 and 2 nanoseconds. So this peak becomes this peak becomes this peak. They propagate by 10 centimeters per nanosecond, in keeping with the velocity, which also has the effect of shifting them by pi over 2 radians per nanosecond. Another way to look at these is to look at a single point in space, the x equal 40 centimeters point, for example, where you'll see that each point has a sinusoid of frequency omega living on it. This makes sense because every point in the transmission line is a delayed version of V in of t. Finally, if you freeze time and move back and forth in x, you'll also see a sinusoid. The same argument applies. Each point in x adds a different amount of delay to a sinusoid that has been going on forever, so we expect to see a different phase at each x value. We can capture the periodicity in t and the periodicity in x with the equation I've written at the bottom of the slide. Each point has cosine omega t running on it, and that's shifted and right in phase by some amount that depends linearly on distance. This raises the question, what's the value of k? To find out, we need to turn to our pictures of sine waves into equations. I've copied over the t equals 0 nanosecond picture for reference. We've already got an easy entry point, which is rewriting V in of t as VZP times the cosine of omega t. And we also wrote an expression for V of xt on the previous page. It's VZP times the cosine of omega t minus kx. It's worth noting that this is a solution to the wave equation because it's just a horizontally stretched version of f of x minus vt. And that's because this argument is x minus vt minus multiplied by some constant. Finally, we need to figure out what the constant k is in this equation. I've written the answer up here and listed a few justifications. The first justification is that we need our solution to solve the wave equation, and the only way for it to do so is for k to be equal to omega over v. Talking through the derivatives in our head, 2 x derivatives will give k squared on the left side of the wave equation, and 2 t derivatives will leave omega squared over v squared on the right side. So k needs to equal omega over v. Second, we can argue that each wavelength of the wave on the line has to result in an additional 2 pi of phase being accrued in the argument of the cosine function. That puts us back at the same point on the wave each period. The easiest way to write that is to say k equals 2 pi over lambda meters, so that if k were equal to lambda, kx would be 2 pi radians. The third way to think about k is to imagine it's telling you the distance per radian on the transmission line, and you can imagine that omega over v is calculating that quantity because omega has units of radians per time and v has units of distance per time. Finally, as a sanity check, if you substitute v equals lambda f into the 2 pi over lambda relation, you get the omega over v relation. The upshot of all of this is that we've defined something like a spatial frequency. K has units of radians per meter, which is analogous to omega having units of radians per second. If t isn't changing, k tells us how far we have to travel on a transmission line before our wave repeats. There's one further complication with how we represent sinusoids on a transmission line, which is that no one remembers high school trigonometry. As a result, trigonometric functions are kind of a pain to work with. We sidestep that mathematical headache using something called an analytic representation, where we let complex exponentials stand in for sinusoids. You can see that we go from our real-world representation over here to our analytic representation over here by replacing cosine of x with e to the jx. We get back to the real world by taking the real part of our analytic representation. However, we often don't really need to go back to the real representation of voltages, because the analytic representation is sufficient for us to keep track of the phase of sinusoids on the line, and that's mostly what we care about when we're doing transmission line math. So, in summary, sinusoidal drives result in sinusoids on transmission lines. Frequency at any point on the transmission line is omega, meaning that we have a sinusoid of frequency omega at every point on the line. The wave number k describes a spatial frequency at one time, and the equations for k are given here. And we'll substitute e to the j omega for cosine of j omega often, which is called an analytic representation.